In this video, we're going to look at another application problem involving absolute value inequalities. We're going to look at a traffic volume problem that's going to turn out to be the classic and or less than, or equal to style problem. So we've got traffic volume. On a given day, the volume of traffic at a busy intersection averages 726 cars per hour. During rush hour, the volume is higher. During off hours, the volume is lower. Find the range of this volume if it never varies by more than 235 cars per hour. And of course, the spirit of the problem is to set it up as an absolute value inequality, because the objective for what we've been doing this week is to be able to solve absolute value problems, equalities and inequalities. So what I want to do is kind of catalog the information I've been given. I'm told that the average volume is 726 cars per hour. The actual volume varies. Sometimes it's higher, sometimes it's lower. The actual volume, which I'll represent with V, so this is going to be our car volume, in cars per hour. So this is the actual number of cars at any given moment of time utilizing the intersection over a course of an hour. And we're told that this volume varies from average by no more than 235. That's the max. So it could be 235 below. It could be 235 cars per hour above. So the way that we set this up is we say, hey, what's the actual volume minus the average volume? And this gives us the variance in car volume. What's actually going on minus the average gives us our variance. The volume varies from average. And we want to kill negative signs because negative car volume doesn't make sense. So I've got my absolute value sign on here. Here's my variance. And we're told that the variance is always less than or equal to the 235. So once I get my absolute value inequality set up, I want to look at the inequality symbol that I have, and I want to identify, am I in an AND situation, or am I in an OR situation? And in this case, because of the less than or equal to symbol, I am in the classic AND situation, which means 235 and negative 235 are going to be my boundary numbers, but my algebraic expression is going to be between those boundary numbers. The variance will be between its bounds. So I get less than or equal to, less than or equal to. And remember, these can't face opposite directions. I never get a situation where this one opens to the right and this one opens to the left. That's not, they have to open in the same direction. Notice it's small number going to larger number, so it's always opening to the right on the number line. And then once I have it set up, I have a three-part inequality that I need to solve, so I add 726 to each of the three parts. If I add 726 to the first part, then I'm going to get, what am I going to get there? I'm going to get 491. When I add 726 to the middle, it will cancel with the minus 726. We'll get a 0. Volume plus 0 is volume, is less than or equal to. And when we add 726 to 235, we're going to get 961. So the traffic volume will always be between 491 cars per hour and 961 cars per hour. If we were to plug 491 in for volume right here, it would equal negative 235, and then the absolute value sign would make it positive 235. And similarly, 961 minus the 726 would be a positive 735. So answering this in a complete sentence, the car volume varies from 491 cars per hour to 961 cars per hour, comma, inclusive. And this word inclusive just tells the reader that the boundary numbers that we're using are included as a possible value for the car volume. And we say that because of the equal to signs on our absolute value inequalities. This equal to part of the inequality says that this number is possible and this number is also possible.